Today, we're going to dive into the architecture of pretty much all modern software, object-oriented programming, or OOP for short. It's a fundamental concept that completely changed how we build our digital world. So yeah, let's just get right into it. Seriously, think about that for a second. As software projects get bigger and, way more complex, how do developers actually manage all those moving parts? A simple list of instructions just isn't going to cut it. You need a blueprint, right? A way to organize everything so that it's stable, scalable, and doesn't just turn into a total mess. Well, this need for structure, it led to a major shift in thinking. See, in the early days, programming was all about actions, just a sequence of commands you'd give the computer. But as ambitions grew, that whole approach started to buckle. It was time for a complete paradigm shift. So on one hand, you have procedural programming. Think of it like a recipe you follow step by step, from the top down. It works, for sure, but it can be super rigid. On the other hand, you have object-oriented programming. Here you build these small self-contained units, these objects, first, and then you assemble them. This bottom-up approach is an absolute game changer. It's more secure because of data hiding, and it's built from the ground up for reusability, which just massively boosts efficiency. And, this didn't happen overnight. This evolution took decades. We started with the raw ones and zeros of machine language, moved through procedural languages like C, and eventually landed on OOP with languages like C++ and Java. The whole focus shifted from just telling the computer what to do to creating these virtual objects that have their own data and their own behaviors. So what is it that gives OOP all this power? Well, it really comes down to four core concepts, which people often call the four pillars. You can think of these as the superpowers that make this whole approach actually work. First up is abstraction. This one is all about simplicity. When you make a phone call, you just dial a number and hit call, right? You don't need to know anything about the cellular signals or the network switches or all the fiber optic cables involved. Abstraction in code is the exact same idea. It hides all the messy internal complexity and just gives you a simple interface to work with. Okay, next we have encapsulation. This pillar is all about bundling and protection. It's the idea of wrapping your data and the code that operates on that data together into a single unit, an object. And what this does is prevent accidental interference from the outside world. A perfect way to think about this is like a medicine capsule. The plastic shell protects what's inside and it controls how it's released. Encapsulation does the same thing for an object's data. It makes sure it can only be accessed through the proper channels, which are its methods. This keeps your code clean and it keeps it secure. Pillar number 3 is inheritance. And this is where that reusability we mentioned earlier really shines. Inheritance lets a new class take on all the properties and methods of an existing class. So you could have a general vehicle class and then create car, truck, and motorcycle classes that inherit from it. It saves you from writing the same code over and over and over again. And finally, we have polymorphism. It sounds a little complicated, but the name literally means many forms. And this powerful concept lets us perform a single action in different ways. For example, you could have one command like make sound, but a dog object would do it by barking, while a cat object would meow. It just makes the code so much more flexible and intuitive. Okay, so we have the 4 pillars. But knowing these concepts is one thing, applying them effectively is a whole other ballgame. That's where the solid principles come in. They're basically the professional's guide to using OOP to build software that's actually easy to maintain and extend on the road. SOLID is an acronym, SOLID, for 5 key design principles that help developers avoid some really common traps. They were introduced by Robert C. Martin, and honestly, they are the bedrock of modern, robust software. Let's just quickly touch on what each of these letters stands for. The S stands for the single responsibility principle. And the idea here is so simple but so powerful. A class should do one thing, and it should do that one thing well. Think about it. If you have one class that handles user logins, database connections, and sending emails, well, a tiny change to the email system could accidentally break the login feature. Separating them just makes the code so much safer to work with. Next is O for the open-closed principle. This means you should be able to add new functionality, that's the open part, without having to change existing working code, that's the closed part. Then we have L, I, and D. L, the Liskov substitution principle, is a fancy way of saying you should be able to swap a parent class with one of its children without breaking anything. I stands for interface segregation, which means it's better to have lots of small, specific interfaces than one giant, clunky one. And finally, D is for dependency inversion, which helps keep your modules from getting too tangled up. Altogether, these principles create systems that are flexible and way easier to maintain. But here's where things get really interesting. Even foundational ideas get debated and refined over time. And while inheritance is one of the pillars of OOP, its practical application has become a pretty hot topic in modern software design. Turns out, not everything is as simple as it first seems. This leads us to a pretty provocative question, one that a lot of professional developers ask. Is inheritance, one of the original superpowers of OOP, actually overrated? This question is really at the heart of a huge debate: composition over inheritance. And this quote from a discussion between software engineers just nails the modern sentiment perfectly. The advice today is often to reach for another tool, composition, before you reach for inheritance. And the reason why? Well, inheritance can create these really rigid relationships that are super hard to change later on. The core difference really boils down to two simple phrases. Inheritance creates an is-a relationship. For example, a rectangle is a shape. This creates a tight hierarchical bond. But composition creates a has-a relationship. A car has a color. See how much more flexible that is? You can easily change the car's color without changing the car itself. You're just composing it from different parts. So why do so many pros prefer composition these days? Well, ultimately, it's all about flexibility. It leads to code that's way easier to maintain and is less likely to break when you make changes down the line. It helps developers avoid getting locked into a rigid family tree of classes that can just become a total nightmare to manage. So what's the big takeaway here? Object-oriented programming isn't some dogma with strict rules you have to follow. It's a toolbox. It's filled with powerful concepts. Inheritance is one of those tools for sure, but so is composition. A great developer knows which tool to use for the job at hand to build something that isn't just functional, but is also elegant and durable. Going from procedural to object-oriented was a massive leap. It shaped the software that runs our entire world today. But technology never, ever stands still. And that leaves us with one final question to think about. What comes next? What's going to be the next big paradigm shift that completely changes the way we think about and write code?